Okay, in this video, I'm going to talk about machine learning. You hear about machine learning a lot these days, and I think it can sound kind of mysterious or a little strange, but it turns out that machine learning is just math. And to prove that it's just math, I'm going to do this the old school way with just a pen and paper to tell you about a topic called logistic regression. And logistic regression is a fairly simple machine learning model, but it does a really good job of illustrating a lot of very fundamental ideas in machine learning, and in many ways is the building block of neural networks. So I think that this is a really good topic to start with. And in this example, the task that we want to learn with logistic regression is called binary classification. And in binary classification, we want to be able to predict whether a data point x belongs to one class, which we'll call y equals 1, or a second class, y equals 0. And to do that, we're going to model the probability that y equals 1 given that data point x. So our approach is to model the probability that y equals 1 given some x. And in this setup, we'll write each observation of y as a lowercase y, which could be equal to 0 or 1, indicating the class label, and a single observation of x as this x with an underline to indicate that it's a vector, and it's a vector containing the elements 1, x1, all the way down to xm. So it's a vector of m plus 1 elements, and the m indicates that we have m different pieces of information and m different numbers or features that describe something about the vector x. And it'll become clear later why we include 1 as the first element of this vector. Okay, so now we need to decide how to actually model this probability. And we do that by assume that the probability that y equals 1 given some data point x is equal to sigma of theta transpose times the vector x, where theta is another vector containing the elements theta 0, theta 1, down to theta m. So it's another vector of m plus 1 elements. We'll get back to what this sigma is in a second. But notice that our model of the probability that y equals 1 is based on a weighted sum of x. Because if we multiply this out, do theta transpose times x, this is going to be theta 0 times 1, which is just theta 0, plus theta 1 times x1, all the way down to theta m times xm. So this is a weighted sum of x. And we can see now that by setting the first element of x equal to 1, we have this intercept or bias term in this weighted sum, and it'll become clear later why we want that. Okay, so we use these m features to say something about the probability that the data point x belongs to the class y equals 1. And we can control the extent to which each of those features contributes to that probability by changing the values of these theta parameters. Then after calculating this weighted sum, we pass it into this sigma function. So what is sigma? Well, notice that if we just calculate this weighted sum, we could actually get any real value. But we want to model a probability which is between 0 and 1. So we need a function that maps all real values to the interval 0, 1. And one function that does that is called the logistic or the sigmoid function, and I'll write it as sigma of z is equal to 1 over 1 plus e to the minus z. And here's what it looks like. We have z here, we're plotting sigma of z. The sigmoid function looks something like this. There's an asymptote at 0, and towards the right, an asymptote at 1, and it passes through the point, the value 0.5. And so as we can see, it'll take any real value z, pass it into this function, and we squash it in between 0 and 1. And there's actually a number of situations in machine learning where we want to do that, including in neural networks. So you'll see this sigmoid function appearing a lot. Okay, so now the question is, what should this theta vector be? Well, that depends on our data. And in order to have a model that does well on a general data point x, which could take on many different values of the various features, we need to base our theta parameters on a variety of x's. And that is called our training data. So in this case, our training data are pairs of x vectors and the corresponding y value, which is a 0, 1, indicating the class that x belongs to. And let's say that we have n of these, so we have I going from 1 to n. And we can use this training data to learn the optimal theta. So what does optimal mean? Well, one reasonable and quite common definition is to say that the optimal theta is the set of parameters that maximizes the probability that of obtaining our training data. And this is exactly what we get by maximizing what is called the likelihood function, which is a function of theta. So we write L of theta, and it's given the entire training data. And it's defined as the joint probability distribution of the entire data set. So all of our training data. And if we assume that our data are independent, then this is just the product of all of the individual probability distributions for each data point. So now we have to express this individual probability distribution in a general way so that it covers two different cases, y being equal to 1 and y being equal to 0. We already know what the probability distribution looks like for y is equal to 1 because that's our modeling assumption. And we can actually write this in kind of a clever way like this. So we have here is the product, and we can see that this part here looks just like our assumption, our modeling assumption for the probability that y is equal to 1. And we can see that if y is equal to 1, then this term is raised to the power of 0 and goes away, so we're covered there. And if y is equal to 0, then this term is raised to the power of 0 and goes away, and we're left with 1 minus the probability that y is equal to 1, which is definitely the probability that y is equal to 0 because this is binary classification and we only have two classes. And if you've studied probability, you might actually recognize that this is the PMF of a Bernoulli random variable. Okay, so we want to maximize this quantity with respect to theta. And that will involve taking a derivative and doing some calculus. But it's pretty hard to find the derivative of this product. So what we can do is actually take the logarithm of it, and we do that, or we can do that because log is a monotonic increasing function. And so the theta values that maximize the log likelihood will also maximize the likelihood. And it's these optimal theta parameters that we really care about. So now we have the log likelihood, which is just the log of the product that we wrote above. And how does this help us? Well, a log of a product is the same thing as the sum of logs. And to get this line, we've also used the properties of logarithms to split this product into a sum and then also take down these exponents. So we get this expression that is a lot more manageable. But it turns out that if we tried to find the gradient of this with respect to theta, we would actually find that there's no closed form solution. And this is a common problem in machine learning. And the standard way of dealing with it is by applying an iterative optimization algorithm like gradient descent, which allows us to find a local minimum. But we actually want to maximize the log likelihood. We want to maximize the probability of obtaining our training data. And so we apply this algorithm on the negative log likelihood. because the theta that minimizes the negative log likelihood is the same as the theta that maximizes the original log likelihood. So we have the negative log likelihood, which is just -1 times the log likelihood. And so we end up with this sum here. There are plenty of great videos out there explaining how gradient descent works. And if it's new to you, you should definitely check those out. But for our problem, we're just going to use it to calculate the optimal value of theta j by iteratively applying this update. We take the current value of theta j and subtract eta times the partial derivative of the negative log likelihood with respect to each theta j. Now, to make things a little easier, we can first find the partial derivative of the negative log likelihood given just a single x and y, a single data point, as opposed to the entire training data. So here we have the negative log likelihood given just a single x and y. But even this is kind of an intimidating derivative, so we can break it into smaller chunks using the chain rule, which is, by the way, also very commonly used when calculating gradients in neural networks. So this is good practice. So the chain rule allows us to, instead of just finding the partial derivative of the negative log likelihood with respect to theta j directly, now we can calculate 3 separate partial derivatives. The first one being respect to p, which we'll say is theta of another variable called z, and then we find the partial of z, finally with respect to theta j, and z is theta transpose times x. So if we find each of these partial derivatives, let's do this first one first. We have the negative log likelihood given a single x and y written in terms of this new variable p, and we end up with minus y over p plus 1 minus y over 1 minus p. And then we find the partial derivative of p with respect to this new variable z. And for this, actually, we can use a convenient property of the sigmoid function, which is that the derivative of the sigmoid is just itself times 1 minus itself. And you can prove that for yourself, but we're going to make use of that here. And then finally, the partial derivative of z, which is our weighted sum, theta transpose times x, is just going to be xj, because xj is the only thing that multiplies theta j. Okay, so now we can take all 3 of those partial derivatives and just multiply them together like this to get the partial derivative of the negative log likelihood with respect to theta j. So let's simplify this further. We can combine these 2 fractions with a common denominator and then also replace the sigmoid of z with p, which is what we define p as. And so we can see that these cancel out, which is nice. Then we end up with minus y plus yp plus p minus yp all times xj. And we can see that these cancel out. And we end up with p minus y times xj. And then we can replace p with the sigmoid of z. And then finally we can plug in z to get the sigmoid of theta transpose times x minus y all times xj. Okay, great. And then finally, remember we calculated this given a single data point xy, but we want the partial derivative given the entire training data. And so for that, all we have to do is sum over the entire training data set. So we sum from I equals 1 to n, and we just sum this expression, but now each of these x and y's is every single data point in our training set. So we index with xi, yi, and then xij here indicates that we're referring to the jth element of the ith data point. Okay, so now we can just plug this derivative directly into our gradient descent formula and apply the algorithm for each theta j parameter. And if we do that, we apply the algorithm iteratively, we obtain our optimal theta parameters, and we'll indicate that they're optimal or fitted parameters by writing a hat on top of each one. So we have optimal theta 0 through theta m, and we put those into a vector, and we'll call that our theta hat vector. And then now we can also write out our final model. So we can say that our final model says that the probability that y equals 1 given a general data point x is equal to the sigmoid function of theta hat transpose times x. But if you remember from the beginning of the video, we want to do logistic regression for binary classification. Here we're predicting a probability, but we want to predict whether a given data point x belongs to the class y equals 1 or y equals 0, not the probability that belongs to y equals 1. And so we can call these predictions, these class predictions, y hat. So how should we define them? Well, why not say that if our estimated probability that x belongs to the class y equals 1, if that estimated probability is greater than 0.5, then we'll predict that x belongs to the class y equals 1. Otherwise, we'll predict it belongs to the class y equals 0. And this 0.5 defines what is called the decision boundary. So it's the boundary between deciding whether a given data point will be classified as y equals 1 or y equals 0. Okay, let's look at a couple of examples. So if we have just a single feature x1, then on a second axis, we can show the corresponding y values to indicate that these values, these circles, belong to the class y equals 0, and these crosses belong to the class y equals 1. And our predicted probabilities for each value of x1 should look something like this due to the sigmoid function. And we can see that the decision boundary will simply be the value of x that corresponds to the probability 0.5. So our decision boundary, if we have just a single feature x1, will be just a single point. If each x vector has two features, x1 and x2, then once again we can use another axis to show the separation between y equals 0 and y equals 1. And so thinking in 3 dimensions here, you can imagine that all of these circles are living in a plane through y equals 0, while the crosses are living in a different plane through y equals 1. And our predicted probabilities for all of these combinations of x1 and x2 will form a kind of sigmoid surface that looks a bit like a wave. And the decision boundary will actually be a straight line that passes through all of these 0.5 probability values. So with a single feature, we have a single point for our decision boundary. With two features, we have a straight line. And we can actually express these decision boundaries, this point and this line, in terms of the theta parameters by solving that equation that defines the decision boundary. So it's just our probability function equal to 0.5. And I'll leave that as an exercise to you if you're interested in. But that's it. So we've done a full walkthrough of a really important machine learning model without even touching a computer. Of course, we need help from a computer to do that gradient descent optimization and calculate our optimal theta parameters. But I hope that I've convinced you that there's nothing particularly special or mysterious about it, and that it really is just math. If you have any questions, please leave them in the comments, and thanks so much for watching.